welcome you all to the webinar on trends in physics. Let me give you the brief bio of a university. SR University, usually termed as SRU, is one among the first 5 private universities declared by Telangana state government in 2020. SRU has created a sustainable innovation ecosystem and attained All India first rank among the private colleges in the Atal ranking of institutions on innovation achievements. SRU attained 134 rank in NIRF in engineering category and also positioned in the rank band of 101 to 150 in the university category for the year 2021. This year has been, the university has been marching ahead and has been in the forefront of imparting high quality technical education, and most of the programs offered are accorded Tier 1 accreditation by NBA. The vision of SR University is to accelerate the pace of transformation and advancement of the regional innovation ecosystem through academic excellence, industry relevance, and social responsibility. In pursuit of this, SRU believes in inclusive growth and encourages interdisciplinary work within and outside the university under the able guidance of our Vice Chancellor. Even though the pandemic has restricted people-to-people interaction, it is the commitment to teaching learning process and interdisciplinary research. The university has been conducting several programs and interactions through the online mode and engaging in collaborative work. In this direction, a webinar series with eminent people as the speakers is planned by the Department of Physics in the fields of cutting-edge research, with the sole aim to serve as a platform for intellectual dialogue and provide insights into the applied aspects, thereby supporting students, researchers, and faculty in carrying out advanced research. The call for this webinar series has received huge response across the length and breadth of the country. There is representation from almost every state of the country. We have few international participants as well from countries like Spain, Philippines, Sharjah, Nigeria, Pakistan, to name a few. We have a wide spectrum of participants which include faculty of all cadres, scientists, engineers, research scholars, and students of both masters and undergraduation from reputed universities or institutes. I would like to put forth here that the ever-increasing demand for energy and much more emphasis on renewable and clean energy, the need for materials with better conversion efficiency and storage has increased tremendously. This scenario has provided vast avenues for basic as well as applied research and also huge potential for commercialization. In the context of its importance, the first lecture in the series is a talk on apprehension of enigmatic nature and control on relaxer behavior in eco-friendly ferroelectric materials for energy storage and other applications by Professor Saket Asthana. We appreciate the participants' interest and enthusiasm to be a part of the learning community and to keep themselves abreast of the latest developments in this field. With the kind of response we have received for this webinar, we plan to conduct many more such events in the future. We wish that you all will be a part of the future activities of the department. I heartily thank the Dean and appreciate the collaborative effort of our department colleagues to bring the event to this level. I acknowledge the efforts of our IT staff who have nicely set up the online platform for the conduction of this webinar. My best wishes to all the participants. Thank you all. Now, I invite Dr. E. Purushottam, Head Department of Physics, to introduce the department to the audience.
Okay, thank you, sir. Good afternoon, all. My name is Dr. E. Purushottam, Department of Physics, School of Sciences, SR University. Honorable Chief Guest of today's program, Vice Chancellor Professor G.R.C. Reddy Garu of our SR University, respected speaker of today's webinar, Professor Saket Asthana Garu, respected and our beloved Dean School of Sciences, Professor Bimal Kumar Sarkar Garu, my dear faculty colleagues, and the most valued participants of this webinar, a warm welcome and good afternoon to all. It gives me immense pleasure to welcome you all to the webinar series on Trends in Physics. I am delighted to see you all in this webinar. The Department of Physics, School of Sciences is one of the pioneering departments at SR University, which was established to impart quality education. So promote applied research and prepare socially responsible graduates. The department is endowed with good number of faculty members possessing doctoral or postdoctoral degree in diverse fields, as well as with rich teaching experience in our department. The faculty of the department undertakes research projects funded by UGC, DST, and SERB, publish research articles in contemporary fields, and are members in professional bodies at the national level. These competent faculty guide the students to have a smooth transition from 10+2, that is intermediate level, to understanding engineering and technology, as well as shape their career. In the recent years, the department has progressed at a rapid pace with the introduction of new courses as well as academic programs. It is my privilege to mention that the department offers PG and PhD programs in physics. The curriculum offered is designed talking the industry requirements as well as the guidelines of the new national education policy into consideration. The department has excellent facilities in the form of well-equipped classrooms, laboratories, department library, and seminar halls. This has helped to impart quality teaching through online mode even during this pandemic situation also. Further, the course content is delivered by incorporating technology into classroom. That is using a right blend of traditional and innovative teaching tools and also focusing on outcome-based education. Our department also celebrates special events such as National Science Day, which helps the students to improve their analytical skills. It is also my privilege to mention that we are going to conduct a national conference in this year. The university is marching ahead in the journey towards educational excellence. So I once again welcome all the aspiring participants. My best wishes to all the participants. Thank you, one and all. Thank you so much. Thank you, all of you. Thank you, sir.
Yeah. Thank you, sir, for briefing about the department and its strengths. Now I welcome Professor Bimal Kumar Sarkar, Dean, School of Sciences, to share his thoughts on the webinar. I should mention here, in fact, he's the guiding force behind the planning and conducting of this webinar series. Sir, please.
Thank you very much. So really, it's a very, very pleasure moment for us. And first of all, we are really very much grateful to our today's our chief guest, our Vice Chancellor, Professor G.R.C. Reddy, and then our very beloved speaker today also, Professor Asthana. He accepted our this invitation and told us that he is ready and interact with us. And then it's really very delightful thing for us also. We are with our all faculty members in the School of Sciences, SR University, and also the Department of Physics, really enriched of the faculty members in different aspect and also a multidimensional way. And most importantly, it is a delightful moment for us that here, I see that this moment 148 participants is here. And even though some students also included here, some students also mentioned something that they are also just maybe class, but one thing I should convey, that this is very important, because whenever university move forward without research, it is meaningless. And as per the vision of the university and great visionary, our vice chancellor, that we have to be improved, we have to be established as very good research institution. Based on this thinking, then research means we need to hear, we need to listen, we need to share research work with renowned researchers, scientists, then only possible to go move forward. Based on this thinking, today webinar is being conducted, where we are very fortunate, and it's a privilege. Professor Saket Asthana, Department of Physics, IIT Hyderabad, given his very precious time to join here as the invited speaker to share some work in this field, in his field, and he will be giving the information and idea regarding mainly some eco-friendly materials for energy storage and other applications. Even though it is very specific one, but I believe that it will be very big motivation and encouragement. All members of the SR University today who are present here, even the other then SR University who are all participants are here, and we got a overwhelming response from the every part of the country, which includes from north to south, Himachal Pradesh to Kanyakumari, from Punjab to Assam, participants registered. So it is a very great moment that Professor Asthana will share, will motivate all of us in the field of research. And also, obviously, it will give us a way for all of us how to move forward in a research direction. So in this respect, I wish a grand success of this webinar today, and it will be very fruitful. I hope, and it is more than my hope, that it will be very, very grand success, obviously. So thank you very much. Once again, welcome all here in this platform. Over to Professor Dr. Rajeshekhan.
Yeah. So thank you, sir, for your valuable thoughts and guidance. Now it's the time to call Mr. K. Srisailam, Assistant Professor of the Department. He will introduce the speaker to the audience. Sir, please.
Thank you, sir. So, good afternoon, everybody. Myself, Srisailam Kanagla, Assistant Professor of Physics, Department of Physics, School of Sciences, SR University. Respected faculty members, research scholars, and students. Today, webinar series on Trends in Physics 1, organized by Department of Physics, School of Sciences, SR University, Warangal. So, it gives me an immense pleasure to introduce and welcome today's resource person, Honorable Professor Saket Asthana, sir. Saket Asthana, sir, is professor at the Department of Physics, IIT Hyderabad, India. He did his MTech in Material Science and Technology in 2001 and secured a gold medal from Indian Institute of Technology, BHU, India. He had worked on manganites during his PhD from Indian Institute of Technology, Bombay. From November 2006 to October 2007, he worked as BK21 postdoctoral researcher at Nano Spintronics Laboratory, Department of Physics, Kyungpook in National University, Daegu, South Korea. He worked on spin crossover molecular materials in the group of Dr. J.F. Littard at ICMCB CNRS Laboratory, Bordeaux, France, from December 2007 to February 2010 as a CEFIPRA and a CNRS researcher. Since March 2010, he has been working in the Department of Physics, Indian Institute of Technology, Hyderabad. Dr. Saket Asthana established Advanced Functional Materials Laboratory at IIT Hyderabad with the support of IIT Hyderabad, DST, SERB, DRDO, Imprint, DAE, CSIR, and JSPS DST projects. Professor Saket has supervised several graduate and postgraduate students, and 5 PhDs have been awarded from his lab. He has close to 90 international publications and several projects. Few recognitions of the work: admitted as the Fellow of Royal Society of Chemistry in year 2021, selected as Associate Editor for Frontiers in Materials, JNCASR Visiting Fellowship the year 2015, DST Young Scientist Award the year 2012, CNRS Researcher, CEFIPRA Postdoctoral Fellow, Brain Korea Postdoctoral Fellow, Dr. K.V. Rao Scientific Society Annual Research Awards for the year 2013-14, invited as a guest professor at ISIR Osaka University during May 2011 to July 2011. Recently, he started collaboration with NIMS Japan. So, sir, research areas: functional materials like ferroic, colossal magnetoresistive, piezo-magnetic, physioluminescence, magnetoluminescence, and multiferrite materials. Studies are focused on oxide-based materials in bulk, composite, and thin film forms. So, applications: magnetic field sensors, piezoelectric energy harvesting, magnetic refrigeration, optoelectronic applications, piezo and magnetophotonics. Thank you very much, sir. Once again, thank you once all.
Yeah, thank you, sir, for the introduction. Now, I would like to welcome the distinguished professor to present his talk on the title. In the context, I would like to inform the participants that if they have any queries, they may type in the chat box along with their name, so that towards the end of the webinar, Professor can take some questions. Professor, please.
Yeah, thank you. Thank you very much. Am I audible?
Yes, yes, sir.
Okay.
Perfect.
Yeah. So first of all, thank you very much for the organizing committee. Starting from the Dr. Rajsekhar, you introduced about the SR University, and then what are the idea behind this university, and then Vice Chancellor vision and everything very nicely. And I would like to thank you, the head of department, Dr. Purushottam, Dr. Vimal, because all of you are so kind, and then inviting me for this kind of event. And then especially right now, especially to Dr. Sri Salam. Okay, so I think he put lot of efforts to note it down everything. Actually, it's and sometimes it's create problem also, that audience will pick up that okay, he is doing this thing also, that thing also. Okay, so thank you very much for nice introduction about myself. And so I will share my screen. And as I mentioned, as Dr. Raja also mentioned, that okay, you can ask the question in between also, because of course this is a webinar, web plus seminar, but it's I will just try to make my presentation in such a way that even if suppose you ask some questions from the different field or sub in the, because the students, they have a lot of curiosity, and then they ask the questions. Okay, so if suppose I am able to say, suppose Dr. Vimal mentioned that okay, right now 150 participants are there across the nation, and from other areas also. So even if I can motivate 10% of those through my presentation, and then that will be good. And then I love to come to Warangal, as I mentioned to Dr. Vimal. So it's you people can also visit us whenever you want. So I'm just sharing my screen. Just tell me that, Dr. If so, can you see my presentation?
Yes, yes. Screen has been shared.
Yes.
Now it is full screen.
Yes, full screen. Yes, sir.
Right now at my place, power cut is there. So let's see. So, but not to worry that it will come in Hyderabad. Generally, that much power cut is not there. So as see, I just my topic. See how I should minimize these things. Some of the, if any candidate is coming, then it is that thing is coming on my screen. So it's okay.
I
Okay,
think,
so
sir, you can drag that folder and keep it aside. The pop-ups you can drag and keep it aside.
the topic is like Dr. Raja also already and Dr. Vinod mentioned that apprehension of the, again this thing is, yeah. So okay, but you people are seeing the slide properly, so that is fine. So even pop-ups are coming, that okay, that is for me only. So yes, so topic is that okay, the understanding of some of the very intriguing features, okay, which is generally happening in the eco-friendly ferroelectric materials. And then if you see in the, I would like to mention the audience, this ferroelectric materials actually you can say electrical analog of the ferromagnetic, because ferromagnetic materials are quite popular. Okay, so most of the people are will be aware of the ferromagnetic material. So these ferroelectric materials for energy storage application, because energy is a lot of demand is there to create the energy and then create the renewable energies resources, and then apart from that there are the other applications. Okay, so I hope somebody is maintaining the timings. Okay, so you can just tell me that whenever timings are, maybe I'm approaching 45 minutes or 50 minutes. Okay. Yeah. So okay. So the early development of the piezoelectric material, actually, this is not that much required, but actually it is always better to give some credit to some people, okay, so who are working in this field, okay, and yes. Am I audible? Because in online presentation, this is sometime
Yes, audible, sir.
audible. Okay. So this is like there was the scientist Pinnes, that okay, he discovered the concept of the pyroelectricity. Okay, so how the voltage is generated, okay, when you increase the change in the temperature. So it was in the 18th century. So this was he observed in the Tomlin, but his interest. So I just want to mention to the audience, especially to the students, that okay, that interest is important. Okay, so this scientist, his interest was in the medicine, so he started doing something, or he completed his degrees. After that, his interest shifted to the physical and mathematical sciences. Okay, then he has done a lot of lot of good work. And then after that, okay, so there are the Curie brothers, so they have discovered the concept of the piezoelectricity. So when you apply the pressure, okay, there will be the development of the charge. That is called the piezoelectric effect. Okay, and the term piezoelectric, this is coming from the word piezo, which is the pressure. Okay, and then it was coined by the Hankel. So this is the brief history. I should not say that okay, it is a complete. This is just a starting point. Okay, so it gives a lot of interest among the students, because directly going to the concept, that is always the good thing, but the logic or the philosophy behind that subject, okay, that is also very important. Okay, so that's why I'm not covering the and everything. So just I'm jumping to the on the what are the some activities are going on in my lab. It's called Advanced Functional Material Lab. So in my lab, actually, it's a group of the people and then students. Actually, most of the things are student driven. Okay, so we discuss some of the concepts and then we see that yeah. Okay, so so we have just this Advanced Functional Material Lab. From here, if you see that, okay, so this logo, can you see that? Okay, that okay. So this logo is also designed by the student. Okay, so I'm not going to into the detail of each and everything of this logo. It has not that much sense also in this presentation. So, but there is a one word, Christo Nasti Durveksham. It means that okay, hard work is never be wasted. Or if you put some efforts, okay, so it will be somewhere, it will be useful for you. Okay, or you can say that okay, you can say that okay, hard work is the shortcut for the success. Okay, because for the people say that there is no not any shortcut. Okay, but if you put that okay, hard work as a noun, their hard work is a shortcut to the success. Okay, so here all color schemes and everything. So I just put your university logo also, that is related to this. Okay, and of course and then you can stop. So you can stop me if you have something to say. Okay, so I just want to see that whether my video is on or not. From where I have to see.
Your screen is visible, sir, but you are not visible.
But okay, so because right now I can see that small this video of yours. So I just also want to see mine. So where I have to click? I think I have minimized somewhere. Okay, okay, I will find it. Yeah, it is there. Yeah, mine is not, but mine is off. That is no problem. Is it okay?
Yeah.
In between, if okay, I will just see. Yeah. So now I can see. Okay. Actually, we have to use the. Okay. So this was the all about the sometimes Dr. Raja, you should from I request from your side you should say that okay something. Okay, so
Yeah,
it will look
definitely.
like that. Sometimes so otherwise it will look like I am telling some story. So complete silence. Okay, so and whether connection is proper or not. So maybe not quickly, but maybe in between sometime. Okay.
Sure.
Thank you. So this is about the logo and the description will be also on my website. And then so what are the activities actually we are doing? So see there are the plenty of the materials. Okay, so thing is that we have to select the materials for some particular applications. Okay, so here sometime I just put in a general theme in a general way, like selection of material. I'm not talking about the ferroelectric, just the selection of the material. It may be thermoelectric, it may be ferroelectric, it may be ferromagnetic, or maybe the photocatalytic materials, or any sort of materials. Okay, so but the selection of material requires lot of understanding, lot of literature search, and what exactly happening in the world. Okay, so by that we select some of the materials and see my domain is narrow, like in a ferroelectric material. In ferroelectric materials, if people are aware, okay, so who are in the ferroelectric field, that in general also lead is toxic. So most of the ferroelectric material which are for the application purpose are lead based. Okay, so we have to be, because handling the lead oxide or lead processing is very, very harmful for the health. So in the European Union, there is a lot of restriction also, but thing is that they have the very good properties. So completely we cannot eliminate them. But at the same time, we can work on the materials that to find out the material who has the properties at least up to, not at par the lead based, but up to the close, very close proximity of those lead based systems. Okay, so selection. And another thing is that, say, for example, this examining the properties of materials. So once you have the material, you should know that, okay, whether it is a metal, whether it is a conductor, whether it is an insulator, or whether it can be it can be useful for sensor, it can be useful for, so for that the material testing is required. Okay, so we use a lot of, like, say, ferroelectric characterization, piezoelectric, apart from the structural, which is the backbone of our research. Okay, so then when we get that, okay, say, suppose, for example, that, okay, this material is good for the energy storage, but of course their properties, of course their numbers are little less, or maybe some other thing which we think that, okay, can be improved further. So for that, there are these, say, for example, which are this our expertise. We do some cation engineering, say, because all elements, they have the different properties. Say, for example, different ionic size, electronegativity, and then how their reaction with the other element and other precursors. Okay, so all these things are involved in the cation engineering. And then microstructure control, like some are the cuboid type, some are the spherical type particles, and those kind of thing. Or if some properties, if they have the influence, they have the influence under the external stimuli. Say, for example, some property, if you apply the electric field, it will change. Okay, if that change can be utilized, that is nothing but that sensing application. Sometimes people ask, what is sensor? Sensor is this only. What are the changes? Okay, and if you can optimize, if you can control that, then you can use that material property for the sensing application. Okay, so here, impact of the external stimuli, I want to tell that, okay, we can change the properties, study the properties under the electric field, temperature, pressure. Okay, it is in general, but generally we study under the electric field, temperature variation, sometime optical properties. So 2-3 external this thing. Okay, we can also consider the magnetic field also as external stimuli, if suppose some magnetic element is there in your system. Okay, so in the title, if you see that, okay, I mentioned the things are eco-friendly. What does it mean by the eco-friendly? Okay, so which is not creating any harmful impact in the environment. At least, if not any improvement, actually our environment and nature from the last 2 years under this pandemic, we have seen that, okay, our nature doesn't want any help from us to improve this thing. Help in the sense, we should not destroy that thing. Okay, so that's why the eco-friendly materials, earth-friendly, are not harmful to the environment. Okay. Another thing is that whatever I said, that ferroelectric material, those materials are called smart materials. This I am trying to link my topic in a more general way, so that a student can understand the thing. Okay. So the smart materials in general, in us also, if suppose there is a group of these students, okay, some student is very laborious. Some student is very laborious. He is good in academics, and another student, he's good in the say, for example, extracurricular activities. But there may be the few students, they are good in academics as well as the extracurricular activities. Then we'll say that those are the smart students. They are in the both. So in the same way for the materials also, we say the smart materials, they have some multifunctionality in the within that. Okay, they can behave like a sensor, they can behave like a actuators. So it's such kind of things. So those materials are called smart materials, like catalysis, photonics, energy. There's several things are there. So we are focusing on some energy materials, some bio application also, our search for the new materials. Okay. And this, of course, if people who are really at this thing, so there are the sustainable development goals are there set by the world organization. Okay, is there. So they have set up 17 goals. Okay, called the sustainable development goals. Okay, so there is also like that some priorities they will define and setting up the goal, and then what are the needs, say for example for the energy for the our infrastructure, sustainable smart cities and all this, and then what are the things are required there. Okay, so there are a lot of funding is also there. Okay, but I am very little aware of that thing also. So if you need, you can just search for that. Okay. Okay. So these are some of the research focus. Okay. So here, if you see that, okay, already I mentioned that, okay, we select some of the materials, okay, and then we explore their structural transitions and how the structure is very important for any material. So if you see that, okay, any material, first of all, you have to find it out that whether that material, whatever you have fabricated or you have synthesized, that are really single phase or not. So you have to do the X-ray diffraction of that. Okay. So some student has Ahmad raised hand for by mistake or any query is there, you can write on the chat box. Maybe tell to this Mansoor Ahmad. So, okay. So these are the structural phase transitions we study. So for that X-ray diffraction, so you should know that, okay, your material is formed. This is a single phase. Okay. Then there is say within each material, there are the several domains. So for example, if you consider the magnetic material, there are the domains. Okay. So domain dynamics and then how it is correlated with the structure. Okay. And if some very fascinating features that I will discuss about the relaxer nature. Okay. And then how we can control that. So these are the fundamental themes on which we work. Okay. And depending on the right is hanged. Hello, can you hear me?
Yes, sir. Go ahead.
Okay. Okay. So now okay. So depending on their properties, okay, these materials can be useful for the different applications. Say suppose here you see that for the joint replacement, or for some refrigeration, for material for the energy harvesting. Okay, so these are some of the facilities with us that we can do some of the basic synthesis and characterization. Okay, so now I will jump to the ferroelectric material. Okay, so these are the prominent application like the dielectric capacitor. Everybody is aware of the like barium titanate based capacitors. Okay, so for like sensors, actuators, energy harvesting, so many thermal imaging, and here you see that energy harvesting. So wherever the movement are there, okay, so our bone, this movement is there. With the movement, actually, it is storing the energy. Okay, so that is the property of this material. Okay, it can behave as an actuator, sensor. Okay, and with the movement, it is store the energy. Okay, and that energy, if it can be used, Okay, it has a very good power density. It can discharge very fast. Okay, so apart from that, several applications, generally we focus on this energy storage, photocatalytic activities, and some of the orthopedic implant. We are not telling that, okay, orthopedic implant maybe any testing kind of thing, but we are proposing that our materials can also be think of to use for electric for these kind of things. So this was the introduction about the energy storage application from the ferroelectric material. So this is my outline of the talk. Okay, so I gave some little pause, so I suppose the attentive audience can read that. Okay, so these are the things. Okay, so introduction on the ferroelectric and piezoelectric materials. Okay, so here you can say that, okay, this is a cartoon. Actually, it's not telling any physical principle here. So here, see here, I'm not going to tell that, okay, what exactly mean by the ferroelectric, what exactly mean by the piezoelectric effect. But in general, if you see that, okay, see in the book also, you can see that, okay, dielectric material. The first line will be dielectric materials are the insulators. So then why dielectric? We should call the insulator. Okay, but they are the phenomena of the bound charges, and then these, if they fill with the electric field, they can polarize also. Okay, so within that, okay, all dielectric, some are piezoelectric with under the pressure, the polarization will be there, charge development will be there, and converse effect is also there when you apply the electric field. Okay, so there will also be strain development. Okay, so this is pyroelectric. Okay, with the temperature change. Okay, so that polarization will be changed, and then ferroelectric. So there is a two polarization. Ground state will be there, and those are the switchable also. Okay, so there, this cartoon shows that these are the people who are working in this field. They are pushing forward for this research for the application on application front. Okay, so now till then this was the introduction. Okay, and now little bit I will just show some of the work from our lab. Okay, so here you see, so we have selected, okay, lead free one system, okay, which is called, in the literature it is called NBT. It is a sodium bismuth titanate. Okay, where the sodium is, I am just going very slow, okay, so that you can at least get some idea about that. Okay, so where sodium is, because if you see, let's see if I can write here, but okay, it will take time, so it's okay. So if you see this, okay, this is a class of one material, it's called the perovskite. Okay, so I would say that, okay, Dr. Raja, my video is clear, my hands are okay.
Yes,
Everything perfect, sir.
Okay. So I just wanted to show this structure. Okay, so because if you consider a small cubicle, okay, you know that, okay, all of you are familiar with the cube. So all corners, okay, atoms are sitting. Okay, those atoms are your sodium and bismuth, complete one. Okay, A. And then at the center, there is a Ti. And on the faces, oxygen. Okay, so this structure is something like that. Okay, so here, why we have selected this material, it has a several importance that, okay, it has a very good polarization. Okay, which we can compare with the lead-based system. Another thing is the depolarization temperature. These words, I can tell you in a very general way that, okay, depolarization temperature means this temperature decide that up to this temperature, your material can behave like a piezoelectric material. You can use this material up to this temperature. Okay, so that is very decent, that up to 200 degrees centigrade. If suppose you can utilize this material. So that is the one thing that we can use. Okay, and this is because its structure is also like a monoclinic lower symmetric structure, so it can accommodate lot of NBT based derivative. Derivative means we can, as I mentioned, that cation engineering. Cation means here, if you see in this, what are the cations? Sodium, bismuth, and titanium. Okay, so these are the cations. If we play along with this, then this is called the cation engine. Okay, so that is the thing. So here, right hand side, if you see that, okay, this is the current, this is electric field. Here, polarization, electric field. Focus on the one. This thing. Okay. Here you see this is the polarization. This is just like a ferromagnetic. If you are aware of the ferromagnetic material, this is ferroelectric. Okay, there are two polarizations are there. They are switchable. So these are called the switching fields. It's called corrosive field. Okay, a switching field. This is called the switching field, and wherever this polarization is changes from this to this, that field is called corrosive field. Okay. Of course, this material also has a drawback that because corrosive field is very high, so it requires a lot of field to switch the domains. Okay, so which is also, but from here you see all plots may look similar to you, but if I will see that, I will say that, okay, this loop is little slanted and then corrosive field is less. So with the, and here it is written that NBT SSR means there are the different processing techniques to make the material, like solid state reaction technique, or some wet chemical methods like sol gel method, combustion method, hydrothermal. So depending on the processing, you can change the property of the material, which can be useful for the different applications. So for example, it is slanted. So in the next slide or after few slides, you'll come to know that, okay, slanted P loop is more useful for the energy storage, and then more saturation kind of thing for the FERM application and other things. Okay, so another prominent material, which is where we have see, I'm mentioning we also have done, but people have also tried. It's not like that this is a new compound. Okay. Okay. Sometimes what happened with the development of the science and technology, some of the things which are already prepared, already studied, but for some other purpose. But with the technological development, right now we are in a situation we can explore some other material property, but with some sophisticated characterizations. Okay, which were not, which might not be possible when these systems were invented 1960 or maybe close to that. So in this system, thing is, you see that, okay, this what depolarization temperature, this earlier it was 200, right now 285, but it's very few people they have proposed this depolarization. It's not very easy to find it out in this system. Okay, so but successfully we have found it. Okay, and that this system has a better breakdown strength. Okay, maybe close to the lead based system. So these two systems I will just explain a little bit more. Okay, so this is their polarization slanted. Here this is the dielectric permittivity versus temperature. So it gives about the structural, it gives about you the transition, okay, phase transition from this maximum, then again drop. Okay, so in this region it is a paraelectric kind of thing, in this region it is a ferroelectric kind of thing. But here you see sometime what happened, if you general thermodynamics, if you have gone through that, you must have seen that, okay, there is a first order phase transition, second order phase transition. Okay, so first order phase transition associated. So yes. Okay. So yeah. So here we can control, as I mentioned, that, okay, these are the techniques, these are the methodology we utilize, that, okay, cation engineering, grain size refinement, variation in processing parameter, okay, precursor variation, and these are the our, you can say that, okay, our expertise. By using that, we frame our strategies to develop materials and then check their applications. Okay. So now, lead-free ferroelectric for energy storage application. Okay. So here you see okay. So this right now you are familiar with this polarization and electric field. Okay. So you are familiar with this plot. You see that, okay, this is this with the increasing field, this is decreasing field, but you see there is some remnant polarization, okay, which is at the electric field 0 is still some polarization there, which is called a remnant polarization. So this green area is the energy, recoverable energy density. So this can be utilized. This much energy you can store and you can discharge it whenever required. Okay. And but this red area is that energy loss. This is not required. This is unwanted. Okay. But thing is that we cannot get rid of completely from this. Okay. So yeah. So here if you see that, okay, we have just wanted to show the trend that, okay, from the lead free ferroelectric material, there is a lot of research is going on, which is number of publications are increasing, okay, drastically. Okay, there's nothing else as to. So here very briefly, I would like to mention that, okay, what is the concept behind energy storage property. Okay, so here thing is that this, if you see the polarization and electric, this is for the linear dielectrics. Okay, so when you apply the electric field, polarizations keep on increasing. Do you think that, okay, this will keep on increasing? No. There will be the limitation. So when breakdown strength will be there, the breakdown voltage, then the sample will be this breakdown will happen, and then it will not be the behave similarly. So polarization will not keep on increasing. Okay, so because then it will not become like an insulator. Okay, so its polarization value is very low. So if you the energy storage density, you have to integrate from here, because you need this reason from 0 to maximum. Okay, but this maximum value is less, not very much, because its breakdown strength is not good. So you will get from here, you will see that, okay, we can use the entire area. But even if you are using entire area, but this value is less. Okay, for that, there are these materials called ferroelectric materials. There, of course, it is showing very less, but its polarization, this P max is far better than this linear dielectrics. But this last thing is which we have to we tackle. Okay, so here if you see that this integration, it is from remnant polarization instead of 0 to P max. So now our requirement is that if we can somehow we can reduce this portion, okay, PR to the 0, close to the 0, okay, less PR, okay, this range we can increase. High breakdown strength, so we can get the P max, okay, less stress is lost. This should become, this should be less, okay, so loss will not be there and PR will be. Okay, so this is the little concept why how ferroelectric materials came in the picture. So in the ferroelectric material, generally, if you see these loops, okay, polarization loop, this is typical ferroelectric loop. So this only blue portion can be utilized for the energy storage. This is anti-ferroelectric. Initially, it will behave like a similar to like a linear dielectric, but at particular field, it will switch their domains, and then it will be then macro domain, and then it will behave like a ferroelectric nature. Okay, so this area is good candidate for the energy storage. But thing is that these materials, most of the materials are lead based. Okay, and their breakdown strength is also not very good. Okay, so in that case, there are this another material called the relaxer ferroelectric. Here, you can see that yellow portion, but it is not like the green one, but still it is better than the normal ferroelectrics. Okay, so and their loop is also very slim. So loss, you are tackling the loss, reducing the PR, and breakdown is also. So we are focusing more on the relaxer kind of ferroelectric. If you just maybe in the next slide, okay. So relaxer, you should from this schematic, you see that okay in the normal ferroelectric, the paraelectric phase, sharp transition, ferroelectric. So if you remember, if you see that okay, there is a very standard material, barium titanate, which we have like this. Here it is like a cubic. This side it is tetragonal. This clear-cut structural transitions, and now here if you see this transition is diffuse. Okay, it is not very sharp. Okay, so in the relaxer state, it's not very sharp, and this transition is frequency dependent also. If you change the frequency, okay, this your maximum temperature will also shift. And this behavior is polarization behavior is like this. Okay, so there are some typical materials are there. Okay, so here you see that transition like the diffuse, and then this. Okay, just for the clear picture, I just mentioned, and then there is some theory behind that. So suppose in the paraelectric state, why it is showing the diffuse transition. So I would say that, okay, here in this dielectric permittivity versus temperature, in the paraelectric state, here particular temperature, which is called the burn temperature. Okay, below that there is a formation of small regions at the nanoscopic length scale, where are the dipoles are there. So now they will form at particular temperature, and then with the decreasing temperature they will start freezing. Okay, they will grow and they will freeze. Okay, and then you no need to worry about that. Okay, what are the words written, ergodic and then non-ergodic. Okay, so that may be little much deeper things. And okay, so there is a formation of nanopolar regions, and then these regions will have the different critical temperature, different transition temperature. So that's why there is a, you can see, distribution of the transition temperature. So that's why it's getting the diffuse phase transition. Okay, for the relaxer it is diffuse phase transition. So, okay, this I can skip because this is a related model to the polar nano regions. Okay, and yeah, so here if you see, okay, so this already I mentioned that. Okay, so this is just for the reading purpose if you want that. Okay, so but see, antiferrous materials are good for the energy storage, but most of them are lead based and their lead is harmful. Okay, so we have to get rid of the lead element there. And then in the lead free material, very few antiferroelectric, but their breakdown strength is also very less. So that's why we have to think about the relaxer ferroelectrics, which has the frequency. It's hanging between. So right now this, okay, so NBT, this is the same system. Why we have selected this material, like the high Curie temperature and polarization value is high, and but D33 is less as compared to lead. Okay, so these are the system instead of this because yeah, so bismuth, because most of the bismuth also behave, because bismuth has a lone pair, the electron like by the lead. Okay, so if you are replacing the lead, so it is also doing the job whatever the lead was meant for. Okay, so here So here actually on this compound, actually this NBT, there was a lot of ambiguity between this 180 to 200 degrees centigrade. People say that it's a ferroelectric phase only. So, but we have seen that there is the two types of ferroelectrics. Not a, in earlier it was only the ferroelectric from room temperature 200 degrees centigrade, only ferroelectric. But we are saying that okay, there are the two different types of ferroelectric phases, and one ferroelectric phase, parent will be like ferroelectric, another will become antiferroelectric. It can be just see that okay, this is the I versus E data of this material. Here you see that okay, because not the different color scheme, but if you see that this is with the increasing temperature, from room temperature to increasing temperature. Here you see that okay, one switching field is there. Slowly this one switching field is converted into two switching fields, and with the increasing temperature, one switching field is going to the another quadrant, -1. Okay, so it resembles that okay, initially there was the ferroelectric phase, only one switching field, but at particular temperature there are the two switching fields. But the second switching field, slowly what is happening, okay, so this is going this way, okay, another one is after particular temperature, before crossing that particular temperature, it is going into the negative quadrant. I hope that okay, I was able to explain it so that you can get it. Otherwise, there are the references where detail this thing is available. You can go to it. Okay. So so it is converted into this. So this can also be shown with the variation of the remnant polarization of temperature. So this will be clear here. If you see that, okay, this is a polarization plot. Here, this peak is there. Slowly, you see the two peaks are coming. So we have explained in that way, there is a ferroelectric domain and there is a formation of the nanopolar region with the increasing temperature. What happened? These regions are also growing, okay, and then they are at before particular temperature, they are in the same direction. So that's why this peak is in this side. Now after that, this cross, and then this phase is becoming antiferroelectric. Okay, so like that, you see that okay, we have the very basic characterization, but how we are analyzing the things, which creates the differences. Okay, so how much you read and how much you relook, and then sometimes what happens, your data will also tell you that okay, I want you analyze me in that way. Okay, you can get the information. So this, as the slide, some slide I have told you that okay, I have shown you that okay, with the different processing, okay, these features can be changed. Okay, so for example, here the graphical representation of the things. So for if you take the solid state method, it can be useful for the capacitor, for the soil gel, it can be useful, that material can be useful. If the same material, if you want to tune from the application point of view, you can vary the methodology, vary their synthesis procedure. And if suppose energy storage, then you can go for the hydrothermal, and for photocatalytic activity, okay, then you can use this. And of course, when you make this material, we have to use the starting material. Say, for example, sodium carbonate, bismuth carbonate, or TiO2, and then say, for example, TiO2 has the two different types of precursor with the different structure. One is anatase, another one rutile. Even if you change that precursor, it has the different, it vary this thing, and then which we have observed in the photocatalytic activities, when we have seen that okay, in case of the, for example, here in case of the rutile, okay, the anatase is found to be the better, reaction rate is better in case of the anatase if you synthesize with that. So that is the role of the precursor, you can say. Okay. Okay, so I will give some pause here, then Okay. So am I audible?
Yeah, sir.
So how much time do I have?
Another 40 minutes, sir.
40 minutes will be too much.
Yeah.
I think any lecture should be not more than 1 hour. So
Yeah,
let's
yeah,
see.
in the
Okay,
middle,
because
getting.
audience will feel bored. So this is the another composition KBT. So here actually initially I told you about this depolarization temperature, which is the temperature. Okay, so below that you can utilize that material for the piezoelectric application. Okay, and another material is that another temperature is that which is called ferroelectric to relaxer transition temperature, because we get the energy storage performance better in during the relaxer regime. Okay, so that temperature is, these two temperatures are very important for any application. And here you see that, okay, measurement of these temperature by very sophisticated techniques. So what we have just put little efforts and then go into and then perform several experiments by using the impedance analyzer or dielectric measurement for the poled and unpoled samples. Poled means you have to pole the sample, because whenever you are talking about the piezoelectric properties, you have to electrically pole the sample. Your all domain orientation should be in the same direction. So for that we have to pole it under the DC applied field for some time, so that maximum domains should be in the same direction. So we have successfully found it like this. See, this is the typical dielectric. Okay, and KBT is because you have seen the slanted loop. So it is another thing is that it's see with the frequency. Okay, this temperature shifted. I told you that, okay, relaxer will show, and the same in the 10 delta also. So even here, these graphs, I can tell you that, okay, it is nothing great here like that. See, you know the Curie V's now. Okay. Okay. So T minus Tm, or sometimes Tc, sometimes theta divided by C. Okay. So here gamma we have used. Gamma has been used. It's called a modified Curie V's law. So when gamma is equal to, say, for example, 1, then it is a standard Curie V's law. It's a normal ferroelectric. It will not be the relaxer ferroelectric. So, but if gamma varies between 1 to 2, then it gives some signature of the relaxer, this frequency dispersion. Okay, so if it is gamma is close to 2, then it is a perfect relaxer. Also, in case of KBT, it is 1.99. It is a good relaxer. Okay. And another thing, you see that, okay, so this is the Vogel-Fulcher relation. I'm not going to see if you clearly, I will not tell you about the Vogel-Fulcher word, then you will say that it is only the exponential relation. Okay. But from here you can get the freezing temperature. Freezing temperature means whatever nanopolar region I told you, it will start freezing. Okay, their orientation will not move. Okay, their dipole orientation will not move. They will start freezing. But when you apply the electric field, they will convert into the microdomains. Okay, so if you see, okay, this graph, these both are the same graph plot, but this is unpoled, this is electrically poled. Then you see that, okay, here in this region, okay, small jump you can see. So this is called a ferroelectric relaxer. Okay, so by this, and then another by when there we have performed another experiment by using the impedance analyzer only, where we got the anti-resonance and resonance peaks, and then disappearance of that peak will give the idea about the depolarization temperature. Okay, so that was the thing that, okay, we want that, okay, the depolarization temperature and ferroelectric to relaxer transition temperature are very important. Sometimes people get confused. They say that the both are the same, but these are not the same. In present case, there is a 10-degree difference has been observed. Okay, so these two temperatures, that we resolved. See, one of our students, he resolved that ambiguity, and I think that paper reference is mentioned there or not, I don't know, but it was Yeah. So this is the polarization plot. Okay. And then if you see that, if you work it out, the energy storage, this performance, you see this composition here. And another thing is that it has the higher depolarization temperature. You can use up to the 285 degrees centigrade. Okay. And if you compare with the other existing compound, this is the say high, very high, but this is what? This is a ternary system, 3 systems, and this is the only the one system. Okay, parent compound. So controlling the properties and reproducibility and other things are challenging when you deal with the binary systems or ternary systems. So in that way, within the parent system, and achieving that energy storage property, and along with the good breakdown strength, this material is very good. And then the cross and these references, you can get the idea about that. Some of the material. Okay, this you can go through this reference if you want to get some idea. Okay. Okay, so now I would just like to mention that, okay, A site disorder lead free. So what do you mean by the A site disorder? So right now you know that, okay, you work on this sodium 0.5 and then bismuth 0.5 or potassium 0.5, bismuth 0.5. At this site or maybe at the TI site, if we change either on this site or on this site, we include some of the more material. These days people are called those, if you are including more elements here, they will say that, okay, high entropy ferroelectrics. Okay, we are also thinking in that direction, some of the things. So that creates the A site disorder. Okay, so this is the structure. So suppose this is this, you can consider that as an octahedra. Okay, so this you can consider as an octahedra. Here, regular octahedron, okay, and like this. And in between, okay, if you suppose sodium bismuth, you have replaced with the potassium, higher ionic size. So what will happen? Octahedra will tilt like this, okay, or some octahedra will tilt like this, 2 and 1 is tilted like this. So to make a periodic this thing, so another octahedra should rotate in this direction. Okay, so there will be the modulated TiO6 octahedra will be there. So don't worry about this tilting, because this gives that, okay, your octahedra is tilting in opposite direction. Okay, along X, Y, and Z directions, 3 directions. So this is called the Glaser notation. If anyone is interested in these kind of things, so they can get the references and that. So in that A site disorder, you see that we put the potassium in between. So what you can see that grain size is drastically reduced. So in that case, drastically reduced, and then we have measured its hardness. It is showing that good hardness value, 10.2 gigapascal, but lesser than BCZT. BCZT is what? Barium, calcium, zirconium, titanate. Okay. And here you see their polarization value is almost constant. Okay. And 40% reduction in EC, as I mentioned earlier, that, okay, we have to reduce the percivity, but retaining the polarization. So without compromising with the ferroelectric or piezoelectric character, here from the PR, we can say that, okay, ferroelectric character, and we increase the hardness. How? Just by the grain size refinement. It is a traditional technique. Here I just want to emphasize, for doing the good work, it's not always true that you need the sophisticated instrumentation, lot of money, and very well developed infrastructure. No, it's your this imagination and your hard work, your consistent effort, and then your reading. Okay, so how you are initially Dr. Vimal mentioned that, okay, then for this you have to share, you have to read, you have to discuss, and all those things. Okay, so discussion is quite important in that case. Okay, so here you see that, okay, grain size. So we thought that, okay, grains, this hardness, its hardness is almost close to the, like those kind of material which people use for the hardness material 203 kind of system. And they use for the bio implant, for the joint replacement kind of thing. So then we thought that, okay, let's see that, okay, can we further improve the hardness? Then instead of potassium, because rubidium is even higher in that group. You see that, okay, sodium, potassium, rubidium, okay, cesium, the little tricky. So rubidium, till rubidium we can try, but it's higher ionic size. So we cannot go like potassium, higher percentage, but a small percentage, with the small percentage, you see that, okay, 10, 100, I think, times this grain size reduction is there. And here you can see the sharp edges. So this is its hardness, if you see, is almost crossed that BCZT. Okay. And then we thought that, okay, let's see that, okay, people are using the Al2O3 kind of only ceramic. But if you use the ferroelectric material, which are the smart materials, they have the sensing as well as the actuating properties. Okay, so thing is that even if you put this material inside the body, then due to the sensing and actuating properties, you can also monitor the health of that implant, because that is very tricky thing that, okay, what happened in the knee and all those things. So but if you replace the things, if you just insert some material and to monitor their health, okay, so what happened, you have to do the reverse surgery. It's not like that. But if you have the material like this ferroelectric and this material with their sensing property, there may be the concept of the self-healing or wear tear kind of performance. Right now the IoT things are there, Internet of the Things, even without direct contact, you can monitor the health of that. So you can avoid the this thing, reverse surgery. Okay, whatever I'm talking about that, okay, this to see the functioning of the implant, you have to do the surgery, 2 times surgery. So which is expensive and then painful because it is happening in the old age. So it is so health monitoring without surgery by using these materials. So this is the biocompatibility studies that, okay, it is biocompatible to the body fluids. Okay, so not any danger for any cells, good cells. Okay, so this work was also highlighted from the energy storage. Also, it has a decent. So that's why I mentioned. So this is created the lot of media coverage was there. So on this, the student Krishna Banerjee. Okay, so he has done this thing. Okay, so this is again, if you see that this is the solid solution of this. Okay, where sodium is 0.25, potassium is 0.25. Here you see that, okay, 2 switching fields are there. Here loop, you can see that it's not like a ferroelectric. Okay, so here you can say not an anti-ferroelectric like, but not like anti-ferroelectric, but there is a combination of both the phases, ferroelectric and anti-ferroelectric. Okay, so here you can see that, okay, they have electrostatic coefficient also, they have got 0.022, which is this coefficient decide that, okay, how much less electric field you need to actuate for the actuator application. Okay, so generally for the lead-based system, it is coming around 0.45 or something, but here it is up to this. And then this coefficient is also very good that, okay, you don't need much electric field to actuate this. Okay, so now next thing is that I discuss about the energy storage and other things. So now here in this place of the bismuth, if we play with little bit of the rare earth composition, rare earth element, then you see. So this is the NBT and BT compound. Okay, this is little different from the subheading which I mentioned. So this is the one of the composition. We have seen that this with the temperature variation, how polarization is changing, and then this can be useful you can also you see that energy storage density. Okay, in the bar graph, I think it will be clear. Okay, it is not given here. So, but this system is showing that this is standard system, but we have explored for the electrocaloric as well as for energy storage. Another thing in this system, this rarer thing, and we have substituted at this side, bismuth. Okay, and this small percentage of ND, it's a 0.01, very small. Okay, why very small? Because we don't want to change this polarization. We want to retain this piezoelectric characteristic, and we want to introduce the optical activity. So here you see when there is not unpoled, and when you poled it with the different electric field, this guy with increasing poled field, this quenching of the PL emission is happening. So if this quenching with this field, okay, it can be useful for the non-destructive testing. Say, for example, if you have this turbine blade, okay, their health monitoring, if you can make a slurry of these materials and then paste it on that, okay, and then if you apply the electric field on that material and it is poled, and then you record, if suppose you record the PL emission, which is this one, okay, so which will be the, if you hold it, okay, when you record, then this PL will be there. If some breaking will happen, okay, it is turbine, some problem is there, then what will happen? This polling field will gone. Once polling field will gone, okay, with that disturbance, then you will get if you do record the PL, you will get this PL. So this difference, if somehow you can optimize, okay, and then do some of the this thing, okay, with the industry, then it can be useful for such kind of monitoring. Okay, this is a figure of merit. Okay, so to decide this is again the thing that, okay, is on student will develop some material where the thermal stability, because thermal stability is also a challenging thing there. Up to what temperature your properties will be retained and can be used, material can be useful for the application. Say, for example, it has a good energy storage density, but not the best, but it can be in the parent system, and then it is a decent breakdown strength, and then good temperature stability. If you see that, okay, up to 90, from 90 to 500, 122. So this is the another work on the same system where you see that, okay, with this anatase, okay, so reaction rate is higher. That initially I have shown that, okay, with this reaction rate is better photocatalytic activity. Okay, so now most of the things related to the energy things are there. So most probably, Dr. Raja, I will take hardly maybe the 10 minutes to finish it.
Yeah, that's okay, sir.
So now I will tell that there is a multiferric properties of the composite. Okay, so because in the audience sometime my student may be there, so if I will not present some of the work of the any student, he will mind that. He will say, sir, you didn't present my work. Okay, so this is the one of my this first premier batch, first batch of the student. He has done on some of the multiferroic system like this bismuth ferrite. Okay, so initial days when we started 2010. Okay, so there were the simultaneous presence of the two ferric orders. Okay, so this is a very simple, like that electric magnetic field stress. So you know that, okay, to understand the concept, okay, piezoelectricity and then covered with stress field as ferroelectricity, ferromagnetic. If these two order parameters are coupled together, it's called a multiferrite. So that student actually, this is not the very prime, the final work of that student. But okay, I got the one slide that, okay, here we have optimized the composition, because here you see that BFO is leaky. So we have optimized some of with the dopant, with the substituent, that, okay, it is showing this thing, and then is saturated loop, even little slanted. Okay, but apart from that, they have the optimized magnetic as well as the this polarization, this thing. So this is the Yes. So this was the, but recently, one of the student, his recent paper is also there, the 2021. He has prepared this NBT-BT, okay, ferroelectric system with the less corrosive field. Another magnetorestrictive system where the magnetorestrictive coefficient is more. So when you mixed two phases, piezoelectric and magnetorestrictive phase, okay, then what will happen if you apply the stress? So their polarization will be different. Okay, so here you see that, okay, these polarization and that will act on the magnetorestrictive phase. Okay, so there when strain is, when you apply the electric field, the strain is developed. That strain will, what will happen? That it will change in the magnetization will happen. Okay, so these things are this magneto-electric coupling. These systems are there. So here you see the two different grains are there. Okay, how successfully, it's very nice microstructure. Okay, so here you see that, okay, their magnetic domains are there, ferroelectric domains are there. When you apply the magnetic field, what will happen to the magnetostic this thing? So they will develop the strain. Okay, so then when you develop the strain, that polarization will happen. So you can control the polarization by magnetic field. You can control the magnetization by electric field. So right now we are thinking about the 2-level logics 0, 1. In that case, you can talk about the 4-level logics also. Okay, so this is a very good work. Okay, so here also he has shown that some with the different percentage of the CFO. Okay, how polarization vary. Okay, and yeah, this he has developed this system. Okay, with the magnetocapacitance, how it is changing. Okay, so on magnetodielectric measurement also evidence that there is a strain mediated, because strain developed through this applying the electric field, there is strain is developed. So that is the, so this is all about the presentation. So summary, in the summary I would like to say like that we focus on some of the materials like energy storage, like for automobile, for thermal stability, piezo photocatalytic activities, hardness for the bioimplant. And this work also, if you just devote like 2 minutes, here it is cycle kind of thing. Okay, so if you can synthesize the different shapes, okay, this is microstructure. Okay, this is not the direct picture, this is our result. Okay, this like a tube kind of thing, and this is the hexagonal kind of, so they have the different this thing. Okay, so here you can see that, okay, they can be with the temperature variation, they can for useful for the energy storage, these things. So here, and then this material can be useful for this if it is a health monitoring. Okay, when it is optically active. Okay, then these days, like there are a lot of things is happening on the flexible piezoelectric. Okay, and the nano generator, when you put the pressure, okay, so it will develop the charges. Okay, so this photo, and one good thing is that if you work, if you use these materials for the technological purpose, okay, and which actually some of the things are happening, okay, like a mobile charger and other things. If you see in the mobile, our mobile also a lot of piezoelectric systems are there, so touch screen and other things. If after use, once these materials are not useful for any device application or something, you just want to throw. If you want to throw the lead-based system, that is harmful. But if you want to throw these materials, say for example in the wastewater, okay, so these material has a lot of good photocatalytic activity also. So what they will do, okay, they will remove the impurities, and they will convert whatever H2O and CO2, and this will be useful for the photosynthesis. And I came to know that from in some plants, their TiO2 can be found. So it is development for this greenery, and from greenery again you can get the TiO2, and you can again make the material, and this cycle is completed. I just try to explain it. Okay, so if concept is going to you, that is my success. So I just want to acknowledge this side, the funding agencies. I think Dr. C. Salam already mentioned everything. That was very surprising. How did he find all those things, details, minute details. So everything wherever I was involved, like BK21 South Korea, CNRS, SCP France, and Osaka invited me for some time, and GSPSDST, of course, but we are having the project. NIMS, I didn't go there, but the proposal was accepted, and then all these are the funding agency to develop the lab, and these are the without these people, okay, it was not possible. So there are the 2, 3, 4 students are, I think, most probably they are going to submit the soon. Okay, so thank you everyone. Yes. So now if some questions are there, oh, so many questions are there. So how should I proceed?
Professor, there was one question I have recorded. Let me present it to you.
Okay.
So, Naisar Selma.
Can I stop the sharing and
yeah. So that person asked, the KBT material stabilize in tetragonal structure at room temperature. And when we vary the temperature and the fraction molar in other applications, I would know what is the stable phase. Will it change or not?
No,
have you justified the choice of your materials?
No, so that is correct. That okay, KBT is in the tetragonal at the room temperature. Okay, so a question is like that: if you increase the temperature, there may be the possibility of some structural changes. So yes, if you perform the dielectric measurement, there will be the structural changes. If not structural changes, then structural modulation will be there. Your ABC parameters may vary. So structural changes, of course, it will be there.
So, Professor, I have one question out of curiosity. Like the parameters have come out really good towards the end of the slides I have seen. Any devices you made regarding the storage part? Have the students made any?
No, actually, I always encourage to the students to develop some devices. Okay, but see, honestly speaking, that I have a limitation. So I limitation in the sense I am a material guy. You can consider me solid state chemist. So I can show the materials properties and applications, possible application, but the device portion is weak in my case. So usually I discuss with the electrical people and other people, but you see that, okay, sometimes maintaining the synergy between the common interest is also very challenging thing. So their interest may be different. So, but I always insist my student that, okay, you try, because trying for the device is a very little work. Whatever they have done great work. And then to develop the device from your material is not that much tricky. But generally what happened, the physics student, actually, I was also the physics student. Okay, so sometimes we are enjoying in the, okay, this peak is going that way and this derivative, that derivative. So they say, yes, sir, I will do. But thing is, so if suppose a good interface is there, then definitely it can be tried. And people are trying actually. We are not trying, but people are trying.
Because I see some good outcome, like most of the things you have done are patentable. That's what my observation over.
So for that, lot of this thing is required.
Yeah. So the other part, like what synthesis techniques you would focus on, like on these materials?
So see, mainly that, okay, we do the solid state techniques, and then some chemical techniques like a sol gel, auto combustion, and then two of our papers, actually one recent paper also, we have seen the precursor role, because precursor initial structure also play a role during the synthesis procedure. So generally these 4 or 5 techniques we use.
Okay.
Yeah. So Professor,
Good afternoon.
hello. You can hear me, sir?
Yes, Malli.
Yeah.
How are you?
I'm good, sir. Yeah. How are you, sir?
Fine. So you joined this university or?
Yeah, I joined here. I'm working here in the Department of Physics, assistant professor. Okay.
Good.
For the last 1 year. Yeah.
Okay, good.
So, for out of curiosity, I have couple of questions, fundamental questions. So, shall I proceed now? Yeah.
Yes.
Sir, you are telling that this NBT is stabilized in at room temperature, monoclinic or rhombohedral. Is there any specific conditions for that?
No. Actually, see, thing is that because rhombohedral and monoclinic. Okay.
Yeah.
So both, if suppose basic unit cell, if you see, okay, so there is a very minor changes are there. Okay. So you cannot say that, okay, see, if you process in that way, then monoclinic, you process in that way rhombohedral. It's a very, very tricky thing. Okay. And even with the so many characterization also clearly figure it out that, okay, CC or R3C. Okay.
Yeah.
Clear distinct is actually, I also have a lot of doubt on that. Okay, so sometimes some people say CC, some people say R3C. So at the basic level, both, if you see the unit cell of the both, the CC is a subgroup of R3C.
Yeah, that I know. But mostly we do this Rietveld analysis. In case of Rietveld analysis, so in most of the case, what structure is resulted? What
most of the cases, if you see clearly, if I remember this the strongest peak, so sometime you see that if it is R3C, okay, so it will be completely symmetric. Okay, but if suppose monoclinic is there, so then with the lower side, if you see that little hump will be there. Generally, most of the people will not figure it out. Okay, whether it is R3C or CC. Okay. But if you go into the detail, okay, and try to see that, okay, the people who are mentioning CC, so if you zoom those peaks, and if you have the data for that, so you will see that, okay, if I am able to draw it here somewhere. If you see, can you see?
I can see that. I can see that, sir. Yeah.
So here, very, if you sum up the papers, say maybe for the good crystallographers like Rajiv Ranjan or something, we see.
Yeah, we know that. We know him. Yeah.
So you can see that. See, we always see that, okay, structure is like that, and then we jump to the material property. Our approach is completely different. Okay.
Yeah.
So if you see, if you follow that or Rodel paper or something, so you will clearly see these even in your data also you can see.
Okay, sir. Thank you, sir. One more question. Like, since we know that this relaxer ferroelectrics has a very slim loop, ferroelectric loop, but even though our compound, but this NBT compound, it has a higher hysteresis of 65 kV per centimeter. So why we are calling it still as a? My question is as a relaxer.
No, we call, but it's a weak.
Okay.
Because think, if you work it out, this gamma value, okay, modified Curie-Weiss law, so it will not come 1.
It won't come 1 actually. Yeah.
So it will come 1.6 or somewhere. It will not come to 1.99 or 2. It will be 1.5 or 1.47 or 1.6. So it is in between 1 to 2.
But in terms of its ferroelectric loop, it is distinct from actual relaxers.
Yes. So that's why this NBT is not considered as a good relaxer. So because it is coming under those parameters, so it is distinguished. It's not a normal ferroelectric because you can see around TD, you can see that frequency dispersion also.
Yes,
that's why you can say that, okay, it belongs to the relaxer, but not the strong relaxer.
Yeah. So one more question I have. So in case of this grain size reduction, as the decrement in grain size, you told that your coercive field decreases
Yes, 40%.
40%. But in principle, as the grain size decreases, in principle, your coercive field should increase due to the grain domain hindering, domain wall motion, due to the hindering of domain wall motion. I would say that. So what is the reason here? Any other specific reason for that?
Didn't explore in that direction, but I think maybe if the size are small, and then maybe if you think about the concept of the dislocation pile up and other things,
Yeah.
okay, like your what kind of planes and other things. So maybe,
Yeah.
but in general, I think our focus was on the polarization, and then at the same time, coercivity is 40% reduced.
Yeah. But there we are telling that its grain size is also reduced. Yeah, but whenever grain, I know that as a fundamental question, whenever grain size reduced, in principle, your domain wall motion is hindered as a result of the.
Yes, you're correct actually, because grain boundary portion is increased.
Yeah.
And then your dislocation pile up and other things. So in general, hardness and other things can be correlated with this thing.
Yeah.
Okay, with this electrical analog, I think the coercive field. Yeah, so you are right. So maybe I think maybe something else maybe happen.
Yeah, that's what. Yeah, okay, sir. Thank you, sir. Thank you so much your kindness and yeah. So it is a very nice track. Yeah.
Thank you. Good luck, Malesh.
Thank you so much. Thank you so much.
So I have one query, sir. This is Bimal.
Yeah,
actually, really many things. We are very benefited to just see this and everything. The result, what you presented, these things. I have one query that just as an extension of Manasham sir.
Yeah.
That if we talk about the grain size, I think there is some correlation between the grain size and also the relaxation also. I mean, if grain size becomes smaller, then their response to the external force is much more swifter. So in that case, is there any kind of time lag or the history is affected also on the grain size?
Yeah, that local domain actually, studying this relaxation behavior is not that much easy actually.
Yeah, that is true, sir.
So, conceptually, we can say that okay, whatever you are telling is correct. Okay, but see, Malesh can see that when we perform the dielectric measurement, cooling heat. I always say that okay, you heat it and reach up to some temperature, record the dielectric and wait, and then record the data with the time. Let's see that okay, it is reproducing the cooling thing or not. Okay.
Yeah.
So that we can do the relaxation study. Or maybe if you do the polarization, say for example, you reached up to the saturation polarization or even remnant polarization, okay, and leave the sample, okay, and then perform with the time. Let's see that, okay, what kind of the relaxation, okay, it's a sigmoidal or stretch polynomial or something. So answering correctly on the Vimal's question, need some experimental proof. So, because because I know your work also.
Yeah.
Dr. Vimal's work that okay is doing a lot of DFT calculations. Okay, so I have gone through that, and that generally I do wherever we go. Okay, we try to see that okay if some collaboration possibility or those things. Okay. So we also have the one good computational faculty, Professor Manish Niranjan. Okay, so a lot of discussion happened. Okay, so once what happened that okay he was telling that okay we are comparing the polarization values. Okay, he said I said okay in NBT we got the 38. Okay, and in his calculation he got the 23. Okay, then he said that it's okay. As an experimentalist, 23, 38, for me it's a difference, good difference. Okay, but he said no, it's okay, because when you do the theoretical this computational calculation, it's really tough, because he said you can do the sodium 0.5 bismuth 0.5. Instead of sodium 0.5, you put sodium 0.4, potassium 0.1. But to run the calculation in computational this thing, it requires high performance computing. Okay, it's not easy.
Yes.
So for us, whatever easy, say for example, doing some substitution and here there, and that is complicated for that.
Yeah, one more thing I know that already I know that this DFT basically it underestimates this polarization quantity, right, sir?
Mm.
Yeah.
Yeah, actually, yeah, underestimate, but sir told that is very true. Whenever we go such kind of more doping and very explicit way, different part, then it needs, that means basically we are talking about a number of atoms per himself is more and more, becomes very complicated. In that case,
Yes. Complicated.
there is some
Yeah.
compromise with the computing also efficiency. That is also important part. That thing.
Yeah. No, but because these days actually this experimental and computational and theoretical, all these things should go together. Because in one conference I met someone that, okay, she was a very renowned this thing, and then I asked that, okay, I was just, when you go in some conferences, you interact with the big people, you say that, okay, I'm working on this and that or something, but sometimes I'm not able to understand a lot of theoretical these things, and then how you manage with the theory and experiment. Then she asked, and then very gently, then she said that, okay, you are in better situation. When I joined, I was the technician there. Okay. And everything you cannot do. So you do whatever best you can do and then collaborate.
Yeah.
Okay. So we also do like that. Okay. The Malesh supervisor is also a very good friend of mine. Okay.
Yeah.
So we also collaborated in some of the fronts. Okay.
Yeah.
So it will give the complete picture actually. If good from the theory side also, because sometimes it's very useful. Sometimes you can predict some of the materials. We can work on that material. Okay, sometimes you can predict, say for example, one of the faculty, they said, okay, my material is so very good thermoelectric material. Then as an experimentalist, we will ask at what pressure, okay, or something, then they will say this much gigapascal or something. Then we'll say, is it possible an experimental thing?
Yeah, okay.
So we have the limitations, and then that is the third stuff. Okay, thank you.
Yeah, Professor, it has been really a wonderful journey you have taken us along within a short period of time, starting from basics to the advances in the field. It was a thorough presentation of your novel research findings to keep us abreast of the latest developments in the field. Thank you very much on behalf of the department, school, and the university. Thank you again. Now,
Thank you.
Now I call upon Dr. B. Malesham, Assistant Professor of the department, who will propose the vote of thanks.
Yeah. Oh, can you hear him, sir? Yeah.
Yes.
Yeah. Good. A warm good afternoon to all, and to our chief guest, Professor G.R. Reddy Garu, valued speaker, Professor Saket Asthana Garu, and all the participants. On behalf of Department of Physics, School of Sciences, SR University, I'm glad to express my vote of thanks. Firstly, I extend my very hearty vote of thanks to Professor J.R. Reddy Garu, Vice Chancellor, SR University, who spared time from his busy schedule to grace this webinar. Then I would like to thank Professor Saket Asthana for giving an excellent talk on lead-free piezoelectric materials for energy storage applications. Sir, it is a very nice talk. We thank you once again. And I would like to thank Professor Bimal Kumar Sarkar, Dean School of Sciences, SR University, for your effort in bringing this valued speaker, Professor Sakes Asthana, to this platform. Then I would like to thank our technical support team, SR University, to extend their support, technical support in organizing this webinar. So I would like to thank all the participants who participated in this event to make this event graceful. I would also thank. Finally, I would also thank all the coordinators who coordinated this event, and all the teaching and non-teaching staff who helped us directly or indirectly in making this webinar event successful. Thank you one and all once again. So one more notice I want to make for the certificate. So we have posted here the link, feedback link. You have to fill up the feedback link, then automatically certificate will be mailed you. Okay. So this is the last notice I want to make on this event. Thank you everyone once again. Sir, Professor Bimal Kumar sir, can we leave the meeting now? Is anything you want to address? Hello. Sir, I cannot hear you.
Yeah. Now, is it audible, sir?
Yeah.
Yes, sir.
Yes. Finally, just everything is done. Everything is done. Final one. We are very grateful to Sir Professor Asthana for his very motivating, encouraging. Everything is there. Not only presentation, and give the department some way, the encouragement. So we are grateful to Sir. So everybody, we are very happy, and finally, also we are very happy to our teamwork and all participants. Already, just it is expressed. So, sir, one request: whenever time is possible to you, please come to Warangal and must visit us. Just we will be very happy.
Yeah,
and
yeah, I will be happy. Yeah.
And your in presence direction to us will be very helpful to us. So this
Yes,
is
sure. Warangal is very close actually. I drove once, so it's not.
Yeah.
So I can come at any time. It's not a problem. Yeah, yeah.
Yes,
And
sir.
then your students and your faculty, Malays is already familiar with my lab and then my work culture. And
Yeah, sir.
everything. Okay.
Yeah.
So you are always welcome. Okay. So my lab is also, you know that, okay, student driven. So whatever a student want to do, I never put any pressure that you have to do this thing, that thing, so that they can evolve, so they can work as an independent researcher. So anytime, whatever help is required from my side, it's also learning experience for me to know that so many people. Earlier, I was aware only in the Warangal, in the NIT, and the physics, some people are working, and then so now, so I came to know that, okay, your university is also doing good. So sure, I'm looking forward to meet, and then whenever you people are coming here, just come to us, and then we can discuss some common proposals or something. Yeah. Thank you very much, Bimalji. Thank you.
Thank you, sir. Thank you so much, sir.
So over to Dr. Rajeshekar. Now, can we go for closing the
Yes, yes.
event?
We can end the meet.
Okay, sir. Okay, sir.
Thank you, Professor.
Thank
Thank you, Professor.